I have a ton of slides in every presentation. I tend to digress. I tend to keep polling and asking you questions like, do you know this? Do you not know this? If you don't know something, be honest about it. You know why? I'll explain it. And you will actually learn something that you did not know before. So there's no way for me to know because we're all diverse set of individuals coming from different spaces. So I can't kind of have the same stream. I'll keep changing the course of the presentation as I go based on the polls that I keep asking you, whether you know this, whether you not know this. Depending on your questions, we may steer the presentation in that direction. All right? So with that, let's kick off. So my name is Sandesh. I've been in the Oracle space for about 20 years. Started off as a DBA, Oracle 716. First week on the job, corrupted the database by trying to auto-extend a data file, which auto-extend was a feature that was introduced officially in 734, but I was brave enough to try using it in 716, corrupted a control file, database crash. Long story short, my manager comes and tells me, you need to sit in a room for 3 months and read the concepts manual. Great. That's how most of us started off as DBAs. I still have the manuals. Nowadays, they don't even ship the manuals anymore. I'll just give you the electronic copies of them. So I've kind of worked across RAC, Data Guard, Enterprise Manager, languages, done consulting assignments, worked on apps. So anything Oracle, I've basically touched. Over the last 2 years, I've actually been responsible for a lot of the diagnosability portion of the database stack, which means alert logs, formats of the logs, data collection, utilities like ORCheck, ExaCheck, TFA. My team is responsible for all of those. We also started working on this thing called AI Ops. What is AI Ops? Everything that you do today as a DBA is basically ops. You're tracking, you're adding table spaces, you're checking for faults, you're trying to do all these things. We use artificial intelligence internally in the autonomous database to do several of those activities. So we'll talk a little bit about that, okay? So the presentation is broken up into a couple of sections. This thing keeps doing weird things. I don't know why, maybe it's a range thing. I've got cartoons for good measure, just to keep us all awake. So when I start off working with AI/ML, that's basically what most people think artificial intelligence is. You take a bunch of algorithms, you throw in a bit of math into it, and that's basically what you get. It's machine learning. The agenda for this session specifically is we'll talk a little bit about the AI Ops platform. That's what I'm responsible for. But at the same time, we'll also touch all the tools and technologies that we internally make use of for doing all the AI Ops stuff that we build. So that if you're an on-prem DBA, you can actually use some of the same kind of knowledge to do these things on your site. And ideas of what are the things that you can do with AI. We'll also talk about what are the other Oracle products that actually use AI and how we use it. And then we'll go to questions and open talk. Why is machine learning suddenly the craze? So if you notice, until like about 3 years ago, everybody was talking about big data, Hadoop, and all that stuff. Suddenly, all that's disappeared. Nobody talks about Hadoop anymore. People talk about Spark, but they talk about Spark in the context of ML, Spark ML, and stuff like that. And nobody really talks about, hey, let's load data into this. Let's move things in Parquet. Let's take stuff in Hadoop, Hive, Pig. Nobody talks about that big data, data lakes conversation anymore. Everything's pivoted towards AI and machine learning. Why is this suddenly so important? First thing is, we're generating gobs of data. An average human generates about a couple of terabytes of data a day from IoT devices, from the Fitbit sensors that you're walking with, from your photographs that you take. You easily generate a couple of terabytes a day. Machine learning has become more accessible. Some of the earliest machine learning algorithms were invented in the 40s, 70s, 90s. Why is this thing suddenly cool now? Because there are libraries for these things. There are library implementations for these things. What does that actually mean? Someone has taken these algorithms and papers that these PhDs wrote, and they've converted them into libraries and API implementations that computer scientists can write or use. So as an engineer, this whole thing becomes a simple API for me. So I can just take an API, write something, make a use of an algorithm. I have no idea what that algorithm actually does, but I know what it expects and what its outcome is. So I'm using this thing to consume for a use case that I have without actually realizing how it works. It's like you're using the database, you don't know how the SGA works, but you're still using it for caching, for parsing cursors, you're doing all this other stuff, but you're using it. And the same way, AI/ML is sort of like this black box that you can actually pass input data into, and do all sorts of interesting things with it because there's a whole bunch of libraries. There's scikit-learn, there's TensorFlow, there's Keras. All these are names of frameworks, languages that are available that are library implementations of these algorithms. So even though you may not be a PhD, so basically, this field is divided into three categories of people. The first one is the PhDs, the ones that are cutting edge, the ones developing the algorithms, the one doing their research in this space, the one writing papers, the ones that are presenting in NIST and all these conferences. The second category is people that build models. We'll talk a little bit about models and what they are and how do you build them. But these are data scientists. What data scientists do is they basically take some information, they take an algorithm, they train it so that the algorithm and builds up a model. The job of the model is to consume the data and give you something useful for whatever. So if I'm a guy working, say, in a payment processing space or a bank, my job is to find fraud in transactions. That's my use case. So I consume transaction data, and my output of that is trying to find fraud using machine learning algorithms. So these are use cases what the people try to build these models for. The third category of people is people that don't understand any of this stuff, but just know they want to consume it as a black box. So that's me working, say, in a bank as a DBA. I have all this data, and I want to run this through ML algorithms to find fraud. I don't really care what this algorithm is. It's a black box as far as I'm concerned to me, but I can use it to be more effective in finding fraud data so that my business can actually catch these frauds a lot more earlier before they happen. Hence, I save them money. So this is a good case of using machine learning as a black box. That's the third category, and it's the most category. That's most of us. And it's okay because majority of the people are in that category. It's very easy to get started with some of this stuff. Just as Docker, someone can get a sandbox with Docker, initialize, have all these algorithms available. Someone can just, today you're going to see, right? You're going to have an autonomous database. You create an OML account, and in a couple of seconds, you can import a JSON file, start writing code in a Zeppelin notebook. And you'll be able to do a class 1 SVM anomaly timeline on some data. I'll tell you what all this is. But basically, you'll see how quickly you'll go from starting off with some of this stuff with a couple of lines of code, next, and you're running some stuff. You look at the output of the code and you realize that's all the code is there. Yep, that's all there is. And you'll actually be doing anomaly detection on some data samples that we have as part of the autonomous database exercise. So it's very easy to get started with some of this stuff. The most interesting thing you have to do is find business use cases. Like how do you get more value? Why is this? It sounds obvious, but it's very counterintuitive. Most people don't do this. What people try to do is, just because everybody else is doing machine learning, people try to apply machine learning to everything. That's absolutely the wrong thing to do. Machine learning has a very specific set of use cases that you're very effective at. You can do most of the other stuff with BI, which is what you've been doing all these years. Building indexes, facts and dimensions, cubes, same stuff. But AI on top of BI is useful for a very small subset of use cases. And when you use it for the right use cases, it does wonders. Use it for the wrong use case, you go nowhere. You actually will expend more resources when trying to use AI versus something that is a simple set of rules, or an expert system is what we call it, which is what most of us have been using all these years. So find the right business use case is usually the most important thing in the case of an ML project. Now, most ML projects go through this particular workflow, including ours. This is good to set some basic fundamentals into place. First thing is, the most important step in any ML workflow is basically cleaning up and preparing the data. That takes the most amount of time. What is it? What do you mean by most amount of time? Like 70 to 80% of the time. It's basically collecting and cleansing data. That's what we do today as DBAs and developers, collecting data, cleaning them up, putting them into a format that can be interchanged somewhere. Either it's in a relational format, or it's a Parquet format, or a JSON format. Somehow it's well defined. It could be schemaless, but it has enough of a schema to be defined to be loading into an ML framework where you can push it up as something called a data frame array. So you have to clean the data source. If the data source is bad, or the quality of data is bad, just like most of the BI reports that we run today, the output's going to be garbage. So 70 to 80% of a task for any machine learning exercise is to basically take the data and cleanse it, and try to ensure that the data quality is important when you're trying to feed this into the model. If you train a model with a wrong piece of data, it's going to give you wrong results. So what does all this other stuff mean? So we'll take a specific example. We'll take an example of fraud detection because that is something that we can all connect with. So the input is transaction information. When the transaction was conducted, what was the amount? Was the person at home when the transaction was conducted? Meaning, are you in Sydney when the transaction was conducted in New Zealand? So it tries to find out where you are. Then was a transaction conducted by a card in person, or was it conducted by remotely, using an online site? So if there's a transaction conducted by a card in person and you're in Sydney and the transaction was done in New Zealand, it's a fraud. These are the kind of inputs that you need to make that determination. These inputs are basically called features to a model. And the process of actually pulling all this information out is called feature extraction. That's the first thing that you see there. Whenever you take input data, you apply an algorithm on top of it, you get something called a model. That model needs input data, which is also called training data, in order to come up to speed. What is training data? When you have a data set, you basically arbitrarily split the data into test and train data. Frameworks know how to do this. So think of it as, I have a table and I just arbitrarily split the table based on some value. Like every row mod 2, take this and put this into this and put this into that. So I use a way to split the data arbitrarily into test and train data. I use the training data along with the algorithm on top of the actual, so training data is what the actual data is. And then you build something called a model. Then I use the testing data to run it through the model to see how it reacts to find what I want to find. So let's go back to the fraud example. So I have inputs, which are basically features. So when the transaction was conducted, how much was it, customer ID, all these input fields. I pass this, and then I have a bunch of outputs that says, this is a fraud, this is not a fraud, this is not a fraud, this is a fraud, this may be a fraud, but this is yes, this is not a fraud. And I pass this into the model. Then I pass the remaining set, which is the testing set, through this and say, okay, now you tell me whether this is a fraud or not. And whatever I have passed it first, it uses that information in order to determine if the rest of the testing data that you are passing to it, is it a fraud or not? So you first telling the algorithm what a fraud is based on these characteristics. After you pass sufficient amount of data to the model, you're basically telling the model, okay, now here's some more data. You tell me whether it's a fraud or not. And that is called the test. While you're testing, there's something called an optimizer function that you apply, which has got nothing to do with the cost-based optimizer that's present within Oracle. It's an optimizer function that you use to basically predict what is a score that corresponds to how this model performed. A very good example is your kid studies something all throughout the year, goes and gives an exam, comes back with a B grade. You're pissed because you know that you have no idea what your kid has studied, but you know that the B grade is not a good grade because that's kind of a universal way of ranking what your kid has done and how he or she has performed. Now, a score output from the optimizer function is what tells you how effectively the machine learning algorithm has performed on the testing data. So what you do is you look at, so you take the input data, which is the training data, you take the algorithm, you apply it on top, you come up with a model, then you run the test data through it. Now, when you're running the test data through the model, there's no training happening. You're just using it based on, so think of the kid example. You studied something, you go to an exam, based on what you have studied, you perform in the exam and you get a grade. You don't learn during the exam. You write something that you've already learned during the exam. Now, if the exam looks exactly like what you studied, that's not good either. If the exam doesn't look like anything that you have studied, that's not good either. That's called overfitting and underfitting the algorithms. So that's why the input data is extremely important on what you use it to train. So let's go back to this. There's input data that's called training data. There's the algorithms that you actually will apply on top of this training data. The output of this result is a model. You will pass test data through this model, and that will tell you the effectiveness of this thing. And then you will basically use the optimizer function to grade how good this thing is. And then if it does not give you the results that you think is what you want, you go back and start the whole cycle again. And you continue training it till it comes to a point where it actually gives you what you want. When The machine learning model is used in a non-training mode. It's called an inference engine. What is an inference engine? Any kind of AI that you're using. You all have phones. When you take pictures on your phones, it tells you there's a cat in this picture. This picture looks like you, and you're in these 20 pictures. That's an inference engine running on your phone. It's not training on your phone. It already understands the concept of machine learning. It understands how to do facial recognition. All it does is it finds a first photo of yours and uses the model to find all the remaining photographs. But it's not training on your phone because it will use copious amounts of CPU on your phone if it does training. Training is a CPU intensive exercise. Not anything that runs as an inference engine is not a very CPU intensive exercise because it's just trying to replay what it is. Remember, when you're preparing for an exam, it's very intensive. When you're giving the exam, it's like, hold your breath. Let's just write this exam and let's get it over with. And you're done. It's not as intensive as preparing for it. So that's basically how this whole ML cycle works. Now, the different categories of machine learning, the one that we particularly make use of is called semi-supervised machine learning. So basically you look for patterns among the data and you use humans to augment or annotate that particular value. So the algorithm just keeps getting better. That's called semi-supervised machine learning. There's also another category that we use, which is also called reinforcement learning. Reinforcement learning is very popularly known, or this category of algorithms is very popularly known in gaming. Computers playing games against you, computers winning against you. The first time the computer loses, it learns all your moves. You play chess, keeps getting better. The next time it uses your moves against you. Then you get better, and the computer gets better, and you get better. At some point, you lose to the computer. So you've heard of all these computers playing, chess and defeating people, computers playing Go, AlphaGo, and defeating people. That is the DeepMind algorithm using reinforcement learning in progress. So reinforcement learning, the way it works is, if you perform successfully, you get this reward. If you don't perform successfully, you get this negative. So the computers don't want to fail. So they keep getting more rewards and they keep finding better ways to beat you. And that's called reinforcement learning. We also use reinforcement learning in our algorithms to find problems. So if you did not find these problems within 5 minutes, then you get negative points. The algorithm tries really hard within the time frame that it's given to try to find as many permutation combinations of the problems that it actually can. So it's a very interesting category of machine learning called reinforcement learning. But majority of the projects we do are basically in semi-supervised machine learning space. Now, there's a distinct difference between machine learning and deep learning. You must have heard these terms. There's machine learning, there's deep learning, there's artificial intelligence. Machine learning algorithms typically fall into 3 major categories. There's clustering, there's classification, and there's regression. Now, what's all this stuff? And there's a whole bunch of algorithms and names on it. Don't bother about it. Here's what you need to understand. The 3 different major categorizations of machine learning problems are basically clustering. Clustering means, is this set of data similar to this set of data? Are these log entries similar to these log entries? Are these faults similar to these faults? Are these flowers similar to these flowers? I don't know they're flowers, but I can tell you they look similar. Those are called clustering problems, which means you bring different sorts of data elements together into categories of buckets that they belong to. And we'll go into more examples as we continue to find use cases in the presentation. But clustering is the first, and all those names below those are different kinds of algorithms that you basically use in this space. If you know, by the way, so how many people here consider themselves to be data scientists or know something about machine learning? Okay, good. So we've got a fairly newbie crowd. Cool. Keep asking me questions. If you want to know more, go more deeper, because 2 hours is not enough to go deep enough into this thing. But I keep trying to give you more concepts. So you can always Google some of this other stuff or anything that you find interesting. But these are just algorithms that perform that particular categorization of machine learning. The second one, which is the most important, is classification. Classification is for when you're trying to find fraud among fraud data. That's a classification problem. When you're given a whole bunch of characteristics, which is called an iris data set of flowers, I'm like, okay, so there's these many petals, there's these many sepals, there's this many thorns, bees come to this thing, it generates nectar, and it smells good. Might be a rose. So that those are called classification problems. So you give a whole bunch of input attributes or predicates, and then you say, predict what this output is. That's a classification kind of a problem. A regression kind of a problem is, I have CPU utilization over a period of time. And then suddenly at 9:30, I get a spike. Is that a spike? Or is that my regular morning user waking up and running his bad job and going away? How do I know this? So regression stands for exactly what the term means. Has it regressed? Standard deviation, mean, gone beyond a certain threshold. The example of this that we use this for is, if I have a 100% CPU utilization condition for a specific customer in the autonomous database, how long before which I know that the customer's workload is going to be significantly affected? That's a use case for us. Now, you might be thinking, hey, as DBAs, I know this stuff. I know my environment. I know morning someone is running a bad job. I know exactly who the bloke is. And I'm going to go kill that job. But that's because you're managing 100, 200, 500, 1,000 databases. We can sometimes manage 30, 40,000 databases. There's no way for me to know who is who. There's no one-to-one equivalence anymore. We get 25 million events a day of all sorts of crazy warnings that as DBAs we get. An OR 600 happened, a table space is about to fill up, a server is about to crash, a 4031 is about to happen. We see this stuff all over the place. The question is, what do I act on? And that's what these algorithms help me make that decision. So if I run a regression training on something, it will tell me that this client, if they run a job for more than 20 minutes at 100% utilization, it usually fails. And that point, I can choose to do one of two things. Warn the customer saying, you keep running this and this is not going to go anywhere. Or I apply auto scaling. So I raise the number of cores, I finish the job, and then I drop the cores back to the original number. And the job finishes off really quick. Of course, the customer ends up paying more, but they also get their job completed versus it dies every day eventually after 20 minutes because it can't continue anymore, things start timing out. So these are the kind of problems where regression is really, really good. And we'll see more examples as we go. But remember this, these are three categories, and this is machine learning. Now you've heard of this other area called neural nets, deep learning, deep nets. These are all different kinds of terms. These are different algorithms. These are not the algorithms we'll be discussing in details today. These are different kind of algorithms. They're used for different categories of problems. They're used for facial recognition, image recognition, speech processing, text-to-speech conversion, translation, all of these. So things like Facebook finding your face, hey Google, turn on the lights. These are the kind of things that make use of deep nets. There's a video surveillance system outside your house that says, hey, your husband's home, make some coffee, that sort of stuff. That's deep nets. That's not these algorithms, usually. It's all deep nets. So when you're talking about a neural network, right, the simplest example of a neural network is what our brains are. A bunch of neurons connected via memory back storage. Our experiences are shaped based on our memories. As a kid, we touch something, we get burnt. The next time we go near a fire, that old memory comes back. And a whole bunch of neurons scream saying, don't touch it. It was not a great experience the last time you did. So our system is a giant memory-backed, multi-layer, complex neural network. And depending on how long our memories last, our experiences are more vivid. That's why, diseases like Alzheimer's and all are pretty fatal for humans, right? Because memory is everything for the neural network that we essentially have. And all our actions we take, whether it is decisions, whether it is experiences, they're all shaped by the past memories that we have. So the synthetic equivalent of our brains or a single neuron is called a perceptron, which was invented in the 40s. We never had the computer power to run that stuff. Now, there are these deep nets, okay? Some of the first algorithms in this space were called LSTMs, or longest short-term memory. Google this, LSTM, as an exercise. These set of algorithms are multiple layer deep nets. Some of the most common applications, especially in the year 2015, was done by Google to improve the performance of the speech recognition by 50%. If you notice today, if you talk to your phones, Google Maps and everything, the voice recognition is flawless. Just before 2015, it was 50% worse. They use LSTMs to significantly improve the quality of the deep net so it understands you better for different languages, for different kinds of syntax, for different kinds of intonations, etymology. It breaks things down very, very effectively. That's what deep nets are really, really good for. So always remember this classification. There's AI and there's deep nets. These stand for multi-layered neural networks that are used for applications like facial recognition, image recognition, searching, hey Siri, hey Google, all of that stuff. And then there's classic machine learning algorithms, which is for stuff like this. Find me fraud. Hey, here's a bunch of characteristics. What kind of flower is this? These are called basic data sets. And these are the three most common there's clustering, there's classification, and there's regression. These are three most common categories of things that you will see as algorithms that people use. How do you train this stuff? We use this thing called AutoML. AutoML, what it does is this entire procedure that I just explained to you. You take something, you train it, and then you find the score is not good enough. And then what are the things you can change? Now remember, go back to your DBA days and remember a performance tuning exercise. What's a performance tuning exercise? You analyze your stats, you run the query, you look at the explain plan. Not good enough. Maybe I need an index. Go build an index. Go back again, run an explain plan. Look at the output. Not good again. Go back. You know what? That init.aura parameter my friend was talking about, I must try that. Change the init.aura parameter, bounce the database, run the query, look at the explain plan. That did it. What is that? It is an iterative method to confirm your performance tuning findings. This is an iterative method to train the model, except you will do many occurrences of these. So for this, someone really has to run through so many different steps in order to complete this. So there are frameworks that basically do this. It's called AutoML. So for AutoML, we just change a couple of inputs. So first of all, you can change the configuration parameters to the model. Now, what is a configuration parameter to the model? The configuration parameters represent, they call hyperparameters. They represent inputs to the algorithms. Hyperparameters to models are init.aura parameters to databases. You change the parameters inputs to the models, and then you basically split your test and train data. Now, sometimes the way you split your test and train data is also very important in the way your model will behave. Once you take all this, you keep training, then you find the performance evaluation, and then you tweak the model again by changing predictions. You again change the test train data splits. Again, you change the algorithms. You try all sorts of combinations. So for getting one good successful model, you could do 1,000 iterations of this stuff. We easily do about 5 to 10,000 iterations every day for each of our models to come up with the one that we want. And once you find the one you want, you take that and then you run that as an inference engine using A/B testing. So think about this. A very good example of this is, I'm trying to find fraud. I build a model, I push it out into my production system, and a whole bunch of fraud cases start coming up. And then people start complaining, saying half the stuff is not fraud because it's crap. Yesterday, you were detecting fraud correctly. Today, it's crap because somewhere the algorithm has mistook a certain set of conditions, which means I got to go back to the drawing board. So what I do is I can go back to yesterday's model and I continue to retrain the current models, making a note that this model that I built and I pushed as part of my A/B testing sucked. And I make note of what did I pick there and avoid that configuration. And I continue to train to find the next model. So these models, the goal of this model is to keep getting better, keep finding more fraud, find it earlier, so the bank does not have a loss and the customer does not experience an inconvenience. Unless it's really a fraud, do not flag it as a fraud. So that's the goal of this model. And this whole exercise continues. So basically take the stuff, change the variants, make a new model, push it out, take user feedback, either leave the model in there or pull the model back and replace it with the older model. All this happens automatically every day. And this happens for every different kind of problem. There's a framework for doing this entire thing. It's called AutoML for us. Internally, that's what we use. We use a whole bunch of libraries. So the machine learning space is rife. It's a combination of infrastructure. It's a combination of proprietary algorithms we use. It's a combination of a ton of open source stuff we use. Proprietary infrastructure, Well, we can write Terraform scripts. We can do infrastructure as code. We can spin up servers, firewalls, networks, and all these kind of things, writing a couple of lines of code in the YAML file. That's great that we use our infrastructure for that. We use autonomous database to store all this data. We use OML directly on top of database data to do all this stuff. But at the same time, I can also use this thing called OML for Pi, which is going to come out maybe in a month or so, where I can write Python code with scikit-learn and combine that with data coming out of an Oracle database. Or I can connect to Spark instances and pull data and run some ML on it. So we work with pretty much everything. The whole ecosystem is still changing. There's new stuff that comes in. Just like every other company, we also pull and play with all sorts of combinations. So within Oracle, what all we are doing? The first thing is the big data appliance. Everybody knows what that is. It's a giant Hadoop appliance. The second one is the visualization cloud. What we do there is we basically look at data, we apply some basic ML to it, and we try to figure out patterns, or say, I have a huge table. I have no idea what this data is, okay? It's got some transaction data, but I don't know what I'm looking for. That's a very common scenario as DBAs we face, or developers that we face. We have a lot of data, but we don't know what to do with it. You know, it's like when someone comes and tells you, hey, you got all this transaction data, I can help you find fraud. Oh, I already find fraud. Oh, wait a second, I can apply some deep nets to find some long frauds, like something that's been going on for a long time that might potentially run into millions. And I can comb this data for you. So, and it's like, oh, I never really thought of doing that with this data. So most of the time, we really have all this data, but we don't know what to do with it. So that's where these kind of things like visualization cloud help. It goes into the data, it finds patterns. It will pull out things like, hey, you know, this transaction for this user happens to transfer $2,000 every Saturday morning on the 3rd. Is that normal? You know, it looks for things like this that you normally never look for. And then it's up to you to decide what you want to do. It's like, you know how you give your photos to Google and it prepares this nice video of your kids doing all sorts of stuff. But you've not really told Google that that's your kid, but it's identified the cutest pictures it can find, and it's made a video out of it and said, hey, what do you think about this video? That's machine learning for trying to extract information out of data and present it to you in a format that you might consider to be useful. And that is called visualization cloud. There's analytics. In the analytics cloud, there's sales, marketing, HCM. There's integration of ML in each and every one of these. Example is, you try to sell something. Hey, it tells you, hey, half of these Facebook friends of yours, they are in these companies, and they probably are good customer. They're potential customers for you. Try to see if you can go and or use them as a sales lead and try to see if you can sell them something. So it's using social media, using connections, using, hey, here's a picture of you and your friend, and that guy is possibly the person running shop at this place. Can you sell something to them? AI can be used in all sorts of crazy ways, whether it is identifying connections, whether it's trying to find somebody that bought something and you want to sell them something complimentary. All sorts of stuff inside the cloud in the enterprise applications can be enabled using AI apps. Then there's obviously data as a service, which is a low-QA, targeted marketing applications. We have huge amounts of data from different things, what people buy, and these things are used to run campaigns to target people. Like, this is what they bought, this is most likely what they might buy, and this stuff, what they might buy, is available on these 20 different places, and we could give them a better deal if that person waited for 3 more days. So it's that sort of thing. So it's not just targeting people for advertising because you can. It's not those stupid ads that we remember seeing, you know, hey, I was looking on some one site, and then every site you troll on that basically follows you there. No, that's not what I'm talking about. I'm talking about something that will truly benefit you, will get you the same item for cheap. I bought something somewhere, an ad follows me that says, return that thing, because you can get this for 30% less in this other location. So that's the sort of targeted marketing application AI that I'm talking about. We have labs. They keep producing different algorithms, different frameworks. AutoML is one of them. So the labs group within Oracle basically works on this. And then there's Autonomous Database, which is a group that I'm part of. The stuff that I work on are these Zeppelin notebooks, as well as all the AIOps applications in the Autonomous Database. So that's what we'll spend the rest of this session on. There's this thing we're releasing. It's called the AI Platform Cloud Service. It's coming soon. What it does, it has a combination of taking projects when you check in something to deploy a complete CI/CD mechanism with version control, pushing the source code, doing the builds, deploying something using Jenkins, pushing out A/B testing, checking if something actually works properly or not, and bringing the results back. It does the whole thing in an automated fashion. While you're at it, it also has integration with a whole bunch of open source tool frameworks. You can write notebooks. There are existing use case templates. What are use case templates? I'm a healthcare guy. Show me all the healthcare AI/ML applications you have. I'm an insurance guy. Show me all the applications you have. Oh yeah, there's a way to find fraud. There's a way to find who might be your next potential customers. There's a way to find who might not be your next potential customers. Like these customers, you should never offer insurance because you're most likely going to lose money. There are models for all of these kind of things. Now, as a person, I just want to use these models. So in different verticals that we are in, these things prove to be very, very useful. And then it also has the ability to basically build and train the models, as well as monitor these models, how they are performing, and then take the models back in case they're not performing. So that's model monitoring, as well as model deployment. So you build something, you deploy, you check if it's working properly, you pull it back. It's a complete end-to-end framework to do all of this stuff. This is a typical end-to-end AI service that does everything that I just told you before, and that's the link for it. We'll concentrate today on this part. ADW, which is one of the autonomous cloud services, which is what we'll have a lab for today afternoon, has a built-in SQL ML tool. What does this mean? It has algorithms built into the DB. You have data that you load into the DB. You can write a couple of lines of SQL and perform machine learning on top of this data and see the results right then and there. And we'll have a couple of examples of how you can do this. Okay, that thing is called a SQL. It's called a SQL ML tool. What are the other things in this space? We've got something called Oracle Advanced Analytics. We're not going to spend too much time on this because we're not going to do most of this. But just to give you an idea, whether you're a SQL, whether you're an R, whether you're a Python developer, there's a graphical user interface for something like an IDE on-prem, or you want to just use the cloud. You have Zeppelin notebooks in the cloud. How many people know what notebooks are? Okay, so just one. So this is kind of a way to write ML code. You basically write it in an HTML page. There are two kinds of products in this space. One is called Zeppelin, which is an open source based Apache Foundation project. Another one is also an open source one. It's called Jupyter, which is actually way more popular, but has some licensing strings tied to it. It is still open source for most people. But so what we have in ADW is Zeppelin. And we'll see how that actually looks as we do the labs. So you load the code, you can run the code in the browser. So all you need is a browser. You can read the exercises in a browser. You can run the code in a browser. You can see the output in a browser. So it's a very convenient way of writing code, and it's called notebooks. Jupyter notebooks, they started off as IPython. It's a project called IPython. So Google that if you want. And basically, if you want to just get started on machine learning on your laptop, there's a classic package called Anaconda. You install Anaconda, and it installs a whole bunch of open source ML libraries onto your system, including Jupyter notebooks. If you don't want to install anything on your box, we do ADW today. There's a Oracle Machine Learning Home where you can get access to notebooks. Every cloud service has its own notebooks. So notebooks are a way for you to interact and write machine learning code against data that's sitting on the object store, in a queue, in a database, anywhere. And you can pull it, you can massage it, you can work on it, and you can give results on it, and you can push it back to whatever source that you want. And we'll do a few examples of those. But that's called notebooks. So just remember this concept. So we're going to make use of Zeppelin notebooks in ADW, but you can also use Jupyter notebooks. They are functionally equivalent. Now, this is kind of a busy slide, but the whole idea is for people who actually know the space, and they're like, do you do expectation maximization? Can I do a class 1 SVM on my data? So this is people who actually do data modeling. They know these algorithms, and they basically want a specific algorithm to train, and they pick a platform depending on what it actually allows you to do. In our case, we don't really care at this point, but these are the kind of things. Always remember classification, clustering, regression. These are three main categories of everything. Anomaly detection is something like if there's a problem, is this a new problem? Is this an old problem? Is this really a problem or is this not a problem? Like, every Monday morning I have a temperature of 100 because I don't want to go to work. That's not an anomaly, that's normal. So I have to find these things. Anomalies are something that don't happen, something that you have to act on, something that you think is not normal. A fraud happens on my credit card on Monday morning. That's an anomaly because I definitely was not doing anything with my credit card on Monday morning. So those kind of things are, you find these things. They call anomaly detection, and that is what the one-class SVM algorithm is very good at. You'll hear this term a lot called time series. Anything that has time and value is basically a time series input. CPU utilization over time, disk performance over time, number of active user sessions over time. Anything that has time and value is called a time series. There's a ton of algorithms on top of time series to do all sorts of interesting value. And we'll look at some use cases, what we do in the autonomous database. I'm going to go through these slides quickly because you're actually going to see the real stuff. So you can see visualizations in this. These are all different screens from this Oracle machine learning library, which we'll do labs on. And then there's a gallery of ML use cases. So remember to look at this gallery when you're doing your labs. So it'll show you all the existing known problems that it actually has algorithms for that you can start using and playing. That's what the code looks like. So this is completely SQL, PL SQL, where they're using a classification algorithm. You'll have something different, but there's prediction and there's a anomaly detection using class 1 SVM in your labs. That's lab 8 and lab 9. So we'll talk about this more when we go into the labs, because when you see something, you can actually relate to it. So one thing that I'm responsible for is the stuff on the right. Detecting faults, collecting information, pinpointing root cause, trying to give warnings when the warning is really a warning versus suppress all the warnings that are not really warnings, and provide a real-time dashboard and the ability to look at some of this stuff. So this is sort of like what we do. We have more than 60 machine learning use cases internally that is currently being worked on. This is sort of like an overall architecture. It's fairly simple. All the machine learning training activity I spoke to you about is done in the top left corner. All the logs, all the metrics, everything goes there. Once the model is built, the inference engine is deployed as a smart collector. It's pushed into the Exadata machines, where it does health checking, real-time fault diagnosis, incident management, encryption, redaction of sensitive data, as well as diagnostic collection. All of that stuff happens on the Exadata machines. All the logs get taken and they get deposited onto the object store because the object store scales infinitely. So you can put all the logs in the object store. All the metrics that correspond to these objects, they get pushed on to multiple sources. There's a dashboard we have where we push all our metrics into. There's also a message broker, which is basically the Oracle streaming service, which uses a Kafka-based implementation for propagating metadata to all the other regions. So any faults that happen, anybody can subscribe to those faults and basically listen onto them and do whatever that they want to do. So as a service owner, I produce a myriad of faults and information about faults. And I can choose to do something with it, or I can choose not to do something with it. So that's what that message broker thing is. There's a admin UI. As a customer, you only get notifications of severe failures. And that's basically this tenant CNS portion down there. And that's it. You won't see any of it. So, and we'll see this as part of the autonomous database lab. Creation of database, scale up, scale down, patching, moving the stuff around. Now this stuff, backups, all this stuff gets completely taken care of, including or 600s, any major faults, online patching, all of that stuff gets completely taken care of by us. And we have several ML use cases for basically understanding, these problems. So, one thing Oracle is really good at is running stuff. When something fails, to fail it over. But one thing we're not really good at is finding these detection thresholds. I'll give you an example. I'm about to have a 4031 in my database, or a 4031, running out of shared pool space. I know I'll run out of it at some point. Now, I don't know whether once I run out of it, is it going to take my database down or not? So, but if I run out of it, I can flush it or I can recycle my instance. But I won't know that till I come to that point. We use AI to identify the cases based on the input characteristics, whether this 4031 is ever going to recover or not. If it's not going to recover, I might as well either recycle it now. So we have the ability to drain sessions. So we'll talk about draining sessions and moving them to another instance in my rack session today evening, of how we do some of this HA part at the back end. And a lot of the stuff you can do yourselves on-prem on your database instances. But the decision of whether should we wait and hope something happens, or is this instance going to really survive it or not? And we use AI to identify those thresholds. And then we act before the fault has completely engulfed us. So we start draining the sessions and moving them out to the other instances, so that when the fault is actually hit, there's nobody on that instance anymore. And we recycle it. So it's the ability to identify these thresholds. That's what the AI is used for. And those are very, very good examples of it. What sort of data do we pull from the machines? We got alert logs, we got health data, we got compliance data, we got availability data from every component that's running underneath. And performance data, workload data, has this workload changed or not? All of this data, all this information is actually collected by us. Capacity data, when is this drive going to run out of space? When is this disk group going to run out of space? We predict things, so things can be changed earlier on. And once all this information is taken, we write this into a telemetry file and we push all this stuff across to the object store, which gets uploaded into a control plane service where we can see everything clear as day. Now you might think, why do we need so much of stuff? We're not talking about 10, 20 databases. We're talking about thousands of databases. So if I want to look at which database do I need to work on next, I have to look at the totality of the entire data center. And I need to look at all these metrics. And if I'm already looking at a log, I've already lost. It's already too much information. I have to look at it's almost like a traffic light. It has to be a red or a green for an entire server, for an entire Exadata rack. And if it's red, means I have to look at it. If it's green, means I don't have to look at it. Small problems, I don't have to look at it. So we have to define it in such a way that I can further say that these are the most important ones I need to look at. Question, yes? Every single server. Every single server. So that telemetry is aggregated across every database that's running on that server. And it pushes it out as a single JSON file across the entire Exadata rack. Not too much, probably less than 0.5% of CPU. Yeah. All these things are lightweight collections. They all touch proc. They're not actively running on the system. They already tap into data that's being collected and pushed out of the system if possible. So a lot of this data, a lot of this ML is not running on the servers. Whenever something happens, the trigger conditions are very light to run. But when we find the fault, we push the data out of the server. So the majority of the resource consumption is pushing the data out of the server. And once the data is out of the server, you can run all the ML algorithms on it. And then you decide whatever you want to do. So all this telemetry generation happens in the control plane, which is not in the DOM view of the server. It pushes all this information out. So that's how we offload, because we don't want to consume half the CPU, half the resources of the box, trying to detect problems in the box. And ML can be pretty expensive if you're running it on the box. So we move it out and try to run all of this stuff as inference engines on the control plane itself. And the thing that's most interesting is you try to identify the faults that are interesting and only push data corresponding to those faults. See, if we were to take every server and push the logs out of every server outside the system and analyze it, we'll probably cross 200 petabytes a year. Today we are crossing 24 a year. Okay, that's how many petabytes of log data and metric data we go through. And we can actually reduce 40 gigs of data to like a kilobyte of data. That's interesting. We throw away all the rest. So all the data has an object service that catalogs things for as long as it can. Now that's only for auditing purposes. But everything else, the actual data which we have analyzed, that we want to use for doing our actual administration is a very, very small, tiny piece of data. We'll see more use cases. So that'll become more clear as we see this stuff. So by default, and this is what happens across all our servers, when a fault is detected, someone gets notified, logs are collected, things get pushed off to an object store. There's no human in this process. There's no human sitting running tar CVFs or anything on these machines. All these machines are detecting faults automatically, and they're all pushing off data to some location. For any fault, any server crash, any database crash, any OR600, any node eviction, all this information is automatically collected and pushed. The system makes a decision. And also the thing, it's very important is, this stuff has to scale at a fleet level. One OR600 happened on one server, or one database. Simultaneously, 5,000 other databases have the same OR600. You don't collect that data from the other databases because you've already collected it once. You need to have the ability to identify that these other 5,000 failures are the same failure, and you catalog them as such. So you significantly reduce the amount of data. So all you do is just recycle this data, just push it out for archival, and that's it. And then you go back, once you find the root cause of this fault, then you push this patch to all the 5,001 servers that you found this fault on. So collection of data is only from one database that generated the fault first. The fix is applied to the fleet as you find it. That's what's interesting. Now, in order to understand that this is the same problem as all the other problems, we've got algorithms for that. We'll spend time looking at about 6 or 7 use cases that we have internally. First is, we go through log files to find the most important events for root cause. This is basically a very simple image of what it is. We go through a whole bunch of stuff. OMC does something very similar in their log analytics package that's available online. But this, we do this specifically for the autonomous database. Some people have asked this for on-prem, and there's a very good chance we'll release an RPM for this, where you can just pass all your database logs, and it'll show you the interesting things in the database logs with information that we have collected. And nobody else can do this because nobody knows how this stuff works internally. You know, we write this code, we know exactly how this works. So it's a subject matter expert training question. So we take all these logs, we order them, and we throw away everything that's not interesting, and we construct an anomaly timeline of everything that represents a fault. So 40 gigabytes of log data can be converted into 1 kilobyte of useful information. So if someone has a fault and has to debug this, they don't bother getting the logs, they don't bother putting them together. Stuff that we do as DBAs and developers today. It's very, very simple. They just click on a screen and say, that's what I want, and that's it. They don't do any of this other stuff that we do. What's the back end here? The training happens first in our labs. So we take the information, we take all the logs, we clean them up, we pull out the entries, the entry feature creation. Remember I told you, the attributes are input to the model. What are the attributes in this case? What logs they are, which instances they came from, is this a process ID, is this an instance ID, is this an Aura error code, is this a CRS error code, is this Aura error code good or bad? You know, these are the kind of things that act as input training to this model. Then there's entry clustering. Entry clustering puts similar things together. I have more slides depicting each of these steps. So let's quickly go through what they are. So basically you build a model and you index the model. And then the last part is what actually gets deployed on the servers, where logs are passed in near real time into the system, and it tells me whether these log lines are good or bad, and throws away everything. All this is real time processing. So I can detect, not just detect a fault, I can tell you it's bad or not. Right then, down to like an accuracy of 1 or 2 seconds, without actually trolling through a whole bunch of CPU. Yes. Splunk ITSI takes a whole bunch of stuff, puts it into a Splunk index, builds an index archive of it, and then runs a whole bunch of ML on it, and then detects patterns. By that time, the fault is long gone. It's not real time. And of course, they don't know how Oracle logs work. So there's no way that thing can be anywhere close to as accurate as what we are building for our stuff. That's a genetic indexing product. It's not, let me put it this way. You can apply basic anomaly detection stuff. These algorithms are very generic. The results are also very generic. They may or may not understand the contextualization behind the products, which means you have to build them with specific ML models that understand those products. The problem with all these generic products is they're really they just give you generic advice. It's like hiring a financial consultant that'll tell you that you should not keep money in your savings bank account and you should, they give you lots of generic advice based on what they see on what generic algorithms have looked at. So the output of a anomaly detection on a web server log and a database log might look very similar when they're completely different products. You need localized information from that product to make the algorithm more specific to that product. Now, I've seen that product, what you're talking about. I've seen their claims. The way I look at it is anybody that builds any ML model on a problem consuming log data from a vendor, if they don't know what that log data contains, that model is garbage. It's like you take your Mercedes-Benz to an Audi dealership and expect them to fix it for you. They can probably drive it. They can't fix it. So that knowledge is going to be very superficial using generic algorithms. And generic algorithms only go this far. So these anomaly detection algorithms are we built for ourselves. Now we don't sell this. This is part of the autonomous database. I'm trying to ship this because many of my customers have asked me for it for free. Install an RPM, put Oracle logs through it, and see what it is. This is built by us because we own the database, we own the products, we own the logs, we know what the faults are. So the models are codified with that. So if anybody tells you that they can build models for somebody else's product, unless they have a person who's been working on that product for several years and has continual contact and knowledge, internal knowledge within the company, that model is generic. This space has close to 25 companies in it. Splunk is just one of them. Go look for anomaly detection or AI ops. You'll find at least 25 companies in your Google search. But like I said, that's what these algorithms are. They are generic algorithms. Yes? I'm trying to ship it as part of TFA. Right now, I'm just stuck in bureaucracy. He can help me clear it off. You see some interesting stuff in his presentation. No, but I'm guessing about 2-3 months at most. So we have TFA releases every 3 months. And all this anomaly detection for logs is a very useful feature that I think the on-prem folks can use. Yeah, all the entire Oracle stack. So that's what a log looks like. We kind of break it down into a generic log statement. Then we basically used other pieces of information, like how many times have we seen this fault? This is fleet knowledge, which nobody has. How common is this fault? How many bugs have we seen on this? How many customers internally, externally have we seen on this? These act as inputs to the model. And we use this to prioritize some of these faults. Then we do record merging and aggregation for the same log signature. Anything that looks similar, like for example, starting up instance ID foo and starting up instance ID bar are similar statements with different instance IDs. I can combine these 2 log entries to form the same thing. Or anything that just has a different error code or a few more words in that log, all these logs are combined, all these log lines are combined together. By default, developers, Oracle developers take a look at this and they look at the output of the machine learning model and they grade it. Is this good? Is this bad? Does it help me solve problems? If not, they completely change the way the model has graded things. And then that input gets fed back into the model and the model rejigs everything and comes back to the developer for the next input. This happens a couple of times. And once the model has done its work and the developer has done his or her work, it's called a labeled data set. So what does first time labeling through functional rules mean? We all have grep scripts that we look for stuff. The grep scripts act as initial input to this whole thing. Then the model goes finding other inputs based on whatever it has correlated. Once this entire thing is complete, it builds a model. The output of the model is called a decision tree classifier. Decision tree is an algorithm. And the way the model is actually stored is using a decision tree. So let me put it this way. What a B tree index is to databases is what a decision tree classifier is to a machine learning model for storage and detection and lookups. This is how we evaluate the score. This is very classic. Now, you don't have to read all of this. Search, just Google for confusion matrix. That's what this is. The F1 scores are a way to basically find out. So there are these 4 inputs, true positive, false negative. So each of these act as input. The accuracy, the precision, and the recall are 3 of the outputs, and the F1 score is a culmination of these. The F1 scores, so sometimes you have to look at the F1 scores, sometimes you have to look at precision, sometimes you have to look at recall, depending on your use case. Like if I'm looking for duplicates in bugs, the algorithm needs to have good recall. If I'm looking for fraud and find as much fraud as I can, I need to look for precision. If I'm looking for flowers, I need to look for F1 scores. So depending on what use case you have to look at a different number as part of this confusion matrix. That's what that whole thing is called. It's a very good Wikipedia page on this. But every model can basically be graded on this. The second use case is how do you find the next best maintenance window when you have this information? This is a very simple thing that we did. Of course, the implementation we have internally is far more complex than this, and we do a lot more stuff than this. But just to give you an idea of what you can do with this. When you have average active session information, we can identify, based on trend seasonality, what times we can run maintenance activities on your database without you really being there. So as DBAs, this is a common question that gets asked to us. Hey, when can I run my maintenance? How about an algorithm that tells you how to do it rather than you guessing? That's what this thing is good at. So what are all these other things here? So everybody knows what an average active session is. The average active session count tells you how many sessions you have active. It's AAS. It's one of the metrics that you can tap in the database. There's CPU, mem, and IO utilization. You take all this information and you stick it into a time series. Then you try to find the trend. The trend is every morning, 9:30 a.m., this user comes in and crashes the database. That's a trend. Then there's seasonality. Seasonality means every morning at 6 a.m. you get up and have your cup of coffee. That's seasonality because every day the same cycle repeats. The AWR seasonality is 24 hours because every 24 hours data recycles. You see the same workload continuously every 24 hours. The residual value is what is evaluated when you apply something called a convolutional matrix with the trend and seasonality value on the original data. So the residual values are the actual values you're interested in. So let me put it this way. I have CPU information for a day that has 20 spikes. If I take 30 days of data, I pass this through a time series decomposition process. I'll be left with 2 spikes. Those 2 spikes are the ones I have to worry about because they're always there. The rest of the spikes, they come and go. So when you take original data, you apply a convolutional filter using a time series decomposition process, you basically will find residuals. The residuals will be the real things. This is a generic algorithm. This anybody can do. So based on this, we identify the period. So what did we do for this? Now, this is a very simple example just to give you an idea of how we play with this information. So that's the original active sessions history data. We apply this convolutional filter on top of it. And then this is the seasonality that is tracked. And it comes up with the best and the worst maintenance periods in this cycle. This is based on 30 days of average active session history data. So it said at 7 o'clock in the evening is when we can run our maintenance. And we started just blindly following this, and it actually works really well. We just have to rerun it every day, and it will give us, for the next day, what's a good time to run maintenance. And it works pretty accurately. It's a very simple thing we wrote over a weekend. But this is how to help identify maintenance windows, where we can run things. Now, why is this important? Because we have thousands of databases. We can't keep asking everybody when your maintenance windows are. We identify them. Now, the best part about this whole thing is you can identify them without looking at data, without looking at SQLs, without looking at anything that is customer specific. This is just observing average active sessions. It's pretty sophisticated as to what you can actually do with this. You can take it to all sorts of crazy levels, but this is a very simple thing of what you can do. If you apply the same algorithm to say redo data, I can identify what's a good time to actually do backups. What happens when I try to take a database backup when the database is busy? What happens? I generate a backup, but what happens? Not just more I/O. Come on, you're on the right track. It takes more CPU, more. No, not freeze the whole instance. Yes, you're all right, but you're not hitting the most important aspect of what happens when you take a database backup. When the database is busy, what is the number one thing that happens? Performance impact, redo. Redo happens. More redo happens. So what does that do with your backups? The backups are bigger, way bigger, 20, 25% bigger. So if I use this algorithm to identify when your low times are running, I can actually reduce the size of your backups significantly because the redo blocks are not written into the backups when the database is not as busy. All I have to do is pass redo generation input information into the same algorithm, and it'll tell me exactly when to take my backups when the least amount of redo is generated. So think about all these other applications of AI that you can actually do in your lab. And this is something that was written by us on a weekend with code that you'll probably find on GitHub today. So the next one is everybody looks at all sorts of combinations of problems. So you're looking at, say, networking issues, and then you're comparing with CPU issues, and you're looking at run queue issues. Now these are all apples, oranges, papayas. They're all different, completely different. You can't compare them. You can't compare CPU utilization to memory consumption. How do you map them together? So what you do is you use this thing called z-scores. It's actually pretty cool. It's a very simple mechanism. And all you do is it basically detects the standard deviation from the mean or a measurement of it. And it gives us the relative unusualness. So it actually does truly allow me to compare apples and oranges. So how does this work? We basically use some kind of a factor. It's called a common factor. And then we graph it. Now here's an example of the first one where, excuse me, CPU consumption, and the lower one is the z-score equivalent. The biggest difference between the top one and the bottom one is the bottom one actually is showing me the real large spikes that I should be looking at. It does, the rest of the other stuff is just noise. But if you look at the top graph, like, what should I look at? You look at the bottom graph, you know exactly what you should look at. That's just passing it through z-scores. Same thing here. I have committed memory, and it shows me the z-score equivalence of that, what I need to look at. The thing that's interesting here is there's all sorts of different values of different things that you're measuring. Proc weighting, if the process is niced or not, is it stuck in IO wait or not? Is it waiting for runtime or not? These are all different z-score equivalents. The interesting thing about all this stuff is you can generate z-scores for all of these absolutely unrelated values. And this is sort of what it looks like. Now you're like, what do I do with this? It's just a bunch of colorful dots. So assume that you're getting home and something doesn't seem right. What do? You look for multiple things. The TV is turned on, usually it's not. My book is not on the table where it's usually supposed to be. I can see my clothes on the bed. I always clean up my clothes and put them back in the cupboard before I leave. The clothes are on the bed. The door lock has some chalk on it, which is usually never the case. There's a pair of slippers outside my house. We never leave our slippers outside our house. I'm looking at all these symptoms, and I'm guessing I'm being robbed. I go outside, I call the cops first before I go in because I know I don't want to get killed if the thief is still in there. So what did I just do? I took multiple things and I found that they were not the normal state I was expecting them at. Each of them has nothing to do with each other. I put all of them together and I concluded that something is wrong in my house. Same thing here. If I look at all these dots, they're just dots. But if I align them and I say, I've got quite a few dots in that same time frame, something's wrong. It doesn't tell me what's wrong. It just tells me something's wrong. So that's a red light at that time. Now I take this information and I combine it with the anomaly timeline. Then I have useful information. The goal of things like this is to not get down to the logs. Look at things at a much higher level of what's wrong. Do I need to really look at this? Do I need to go down to the logs and look at the faults? But this thing really helps me. So this whole thing is just one giant red light that tells me that something is wrong in this entire server. Looking at all the different characteristics. And I can just line them up. And in between, there's a lot of other z-score variations, which I don't care about, because they're not happening at the same time. Extremely powerful for us. Another one is we also use ML to discover duplicate bugs. We also use this internally within the instance. So when you guys submit a service request, this is what we see. It has everything about your system that we want to know about. We know more about your system than you will know about your system in 5 to 10 seconds. How many servers you have, what patches you've applied, what your disk utilization is, which components are failing. Is your database having more problems as compared to your clusterware? What stuff have you changed over the last couple of months? Everything is tracked for us to quickly identify the root cause. Events for timeline, anomaly detection, what are the faults, what are the recommendations, and all the duplicate bugs that are associated with the problems that you're currently having. All of this stuff comes up in one single screen for us. We can take your logs, we can click, we can merge them up, we can do all sorts of stuff with it. So we have the ability to simultaneously look for duplicate bugs the moment you submit a service request to us. Of course, you can do this too. If you upload a TFA package, you can actually do this too. But this is what essentially we see. And what we do is we basically use something called logistical regression internally to identify duplicate bugs. We train on these, and the model uses a bunch of input attributes like error stacks, cursor information, problem description, and a whole bunch of other stuff to identify which possible duplicate bug it is. This is very useful for us because we get hundreds and thousands of errors, and we want to find out quickly if these are known issues or not. And all those databases get scheduled for patch applications. So nobody's looking at this. It gets automatically applied. Another one is we look at a series of events and we try to identify if this event is happening. We won't go into too much details on this. There are many different kinds of algorithms. We use something called HTM. We use something called finite state automata to identify what is exactly going on. And based on the first couple of steps, like if I see these two messages, the database instance is going to crash, is an example of this thing. This one is the only one where we make use of deep nets. We use LSTMs for this. So this is like a log entry, and that's all the knowledge IDs that correspond to them. And that's a central event, and we correlate and quickly find out what is happening and when this happens. And this is different for different servers, by the way. It's different for different servers, it's different for different databases, because different databases behave differently. Like if I have a large database allocation, it will behave completely differently as compared to have PDBs. I have 5,000 PDBs running here. Those databases will behave completely differently as compared to one database that has a 5 terabyte SGA. So each of these models has to function differently depending on the faults in that particular system. And based on that, we generate signatures, and we match these signatures against something that's already generated to look for faults before they have happened. This is a tool called the Cluster Health Advisor. It was released with 12.2. It's been out there for a while. It detects most common rack issues. We'll spend some time on this actually. I'm not going to cover this because we're going to spend some time on this in the rack session. But the reason it's in this deck is we use it to detect outliers from all the performance issues in our cloud, and we use something called Bayesian networks. By the way, all the slides will be available on my LinkedIn/SlideShare after I'm done with the last city, as well as Francisco is also going to make them available at some point in time. Okay, so you don't have to take pictures of the slides and stuff like that. You will get all of these slides. So we make use of Bayesian networks here to identify root cause. And this acts as one of the inputs to the several different methods that I described that we look for problems internally in the cloud. But we'll talk about this in more detail when we're doing the rack session. So this is just all the kind of algorithms and technology we use. We used to use ELK. We're slowly moving away from ELK. We use Lucene for scaling out. That works way better for most of our stuff. And these are the other algorithms that we basically make use of for detecting faults, for anomaly timeline, for prognosis. The last one is how do you detect workload issues? So let me go to this. This actually gives you a better idea of what it is. So we capture stuff in 1 minute windows across 5 minutes. And then once we do this, we use 3 different algorithms to identify which is a good baseline. And each of the algorithms gives us a score. Whichever gives us the better score, we use those results. And the algorithms are isolation forest, one-class SVM, as well as local outlier factor. The way this works is actually very simple. We capture all this information from the PDBs and the CDBs. Once the metrics are taken, we can capture ancillary ASH data to support our analysis in case we do find a problem. We train this. Now this training happens every now and then. This is fairly constant. And then whichever model gives us the highest confidence, as long as it's above 95%, we make use of that model. And basically our testing has shown that 7 days of information is necessary for doing this. And there's a rolling window of 30 days of data to account for seasonality. So now you know trend, seasonality, time series. It's important you know these terms. You can build on it. Because most of machine learning is based on terms like this. Then, in one class SVM, we basically take the workload data. We try to find what is the normal behavior across dimensions. And any new observations that indicate that these are anomalies, they're classified and they're pushed out of all the regular data. So in this case, it identifies that those 2 metrics are basically out of classification. That's how one class SVM works. Local outlier factor works slightly differently. You take each anomaly data point and you calculate its distance from that point further away from all the other data points to find out how isolated it is. Now this distance is basically a distance between that particular point and all of its nearest neighbors. Then any anomalous data point is going to have greater distance than its closest neighbors as compared to the other points. And then once you do that, you've identified exactly which one is the anomaly. And this is how local outlier factor as an algorithm works. Of course, it's way more complicated than this. I'm making it a lot more simpler so that you can actually understand conceptually what these algorithms are. So either it's this or a crazy PhD paper that you have to read, which you may probably never come out of. Isn't this simple? Machine learning is simple, guys. Put that in your heads. You don't have to go through complex stuff. You know, as long as you conceptually got what I told you, you've learned something that took me 6 months to learn through the PhD papers. So then subject matter experts look at this stuff and say, hey, does this make any sense or not? And then they work with the models to release the right models. The whole thing put together, something is captured, metrics are evaluated. If there's no primary model, then the SME rules are used. SME stands for subject matter expert. If the models are there with more than 95% of confidence, they're used to identify the workloads are an outlier. And then the anomalies are raised. When the anomalies are raised, the corresponding ASH reports that come from those anomalies is also forwarded. So the ops person can look at this information. This is workload classification. And this, I think, Connor's going to talk a little bit about this, which is the 19C feature for automated indexes. To conclude, ML's here to stay. It's just getting started. You'll see this everywhere. The last 2.5 years of stuff that has happened basically dwarfs the last 30, 40, 50 years worth of advancements. I mean, this space is growing. It's not, so here's the thing, right? We're not inventing new stuff, but it's getting better. Like, for example, you look at a Tesla, it's still a car, it's still four wheels, it still looks like a car that was built by Ford in the early 1900s. But it's got a computer in it, you know, it does self-driving, it has new features, but it's still a car and it looks like one that was built 50 years ago. So machine learning is like that. Each of the individual spaces, there's massive disruption happening, but the fundamental algorithms that people use were still invented in the 50s, in the 70s, and the 90s, and lots of incremental improvements over these algorithms are being made because of the availability of servers, because of the availability of open data sets. There's a site called Kaggle, and people look at this and find a whole bunch of open data sets. A lot of people have taken existing problems and democratized these data sets and pushed them to Kaggle. So the thing about these flowers examples I keep telling you about, it's called the iris data set. Google it, iris data set. You can download this data set. You can run all sorts of pre-code against it. It's a very good way to learn these kind of things. So Kaggle has about at least 500 to 600 plus data sets. Massive data sets, couple of gigabytes, solving different kinds of problems, looking for human genome issues, looking for cancer tumors in a whole bunch of x-rays. There's a whole bunch of open source data sets that people have pushed there. That's the best way to start learning some of this stuff. You need to identify as data custodians of your companies to find new use cases of how you can derive better value from data. That's the number one thing as DBAs and developers that you can do. Find value from data using ML. You already own the data. You already know the data. You already know how it's stored. You already run BI reports on it. AI is the next step that runs on top of BI to make these things even more useful. Modeling an ML infrastructure like AutoML is going to become standard. You do not need to learn it. There's going to be something that's going to help you do this and iterate through this training exercise constantly. Getting the right data is very important to train for the right outcome. If your data is crap, your model output is crap. Usually models require tons of data to train. The new algorithms that's coming out in the last couple of years are getting smarter and smarter. They require lesser data to train. And you'll see more and more of this happening, where you'll need copious amounts of data to train something. A little data, and you'll start seeing results from some of these algorithms. They're really good at predicting some of these use cases. Most enterprise applications are already using ML in some form or the other. You're surrounded by it. You're using Google Maps to go somewhere, it's using ML. You're saying hello Siri, hello Alexa, hello Google, using ML. Using any kind of translation, you're using ML. You walk outside your house, a smart camera tracks you, identifies you, catalogs you, classifies you or misclassifies you as a cat once in a while. That happens too, but that's also ML. So video surveillance, you're watching something on Netflix, you're doing your preferences using ML. So everything around you, from your fraud detection in your bank accounts, to the movies you watch, to the places you walk, to the cameras that scan you, to the airport places that you go and you scan your thing, everything uses ML. You're surrounded by it. And this is only going to get more and more deeper. So autonomous self-driving cars, smart AI built into enterprise applications, databases that run themselves are just the beginning of this space. So don't be scared of ML, get into it. What I've given you today is a very brief primer. And the labs that we're going to do in the afternoon will take you one step deeper into it, where I'll explain more practical examples as we go through it. So you can connect the dots with what I have taught. Now that you've sat through this whole session, thank you for sitting here. And hopefully nobody has dozed off. Because now I have Connor to wake everybody up. So thank you guys. And do we have tea now? Yeah. I mean, I'm around if you have more questions. Thank you. Can I get rid of the cyborg thing?